Today we have a sharp inequality, and by that I mean that the left-hand side is just barely greater than the right-hand side. Now, just from what we know about fractions, we can see that the right-hand side has to be less than 0.2 since 8 over 40 is equal to 0.2, right? 8 over 40 is the same as, 4 over 40? So, I mean, 8 over 40 reduces to what? 2 over 10, which is 0.2, but this is 8 over 43, right? Okay, so this guy right here is definitely less than 0.2, but notice, so is the left-hand side. The left-hand side would have to be less than 0.2. Now, that's easy to see when you know that this part right here is 0.05. 1 over 20 just reduces to 0.05, right? So you can, just by some fairly crude estimates, see that this is a fairly sharp inequality, okay? Now, what we're going to use to prove this is something that's referred to as the AMGM inequality. It stands for arithmetic mean / geometric mean. Now, the arithmetic mean is with respect to addition. Geometric mean is respect to multiplication. Okay. Now let's work just a concrete example. Let me pick some numbers here that work out rather nicely. We'll just do the n equals 2 case in the name of time and space. So for n equals 2, we might consider, let's say, 4 plus 9 over 2. Now, y'all, the ace of i's here have to be positive for this to hold up. Let me write that in here, which they are in this case, but the ace of i's have to be, I guess, non-negative is a better way of putting that. Greater than or equal to 0, I believe, okay? Now, so just applying the n equals 2 case to these numbers, we get 4 plus 9 over 2. And I'm going to write strictly greater than the square root, and I'll put the square root indice of 2 in there just for emphasis. This 2 is a divisor here. Here it's the index of the radical. Now 4 times 9 is certainly 36. I'll just write 4 times 9 here. But of course this is equal to 6, right? It's equal to 6. And so you see you got a strict inequality here. You have a strict inequality. 4 plus 9 over 2 is 13 over 2, which is certainly greater than 6, right? Okay, so that's an example. That's kind of a sanity check on this guy called the arithmetic mean, geometric mean inequality. This is the product notation. You take the product of the numbers, which is what we did right here, 4 times 9. Okay, so let's see how we can use this to establish the veracity of this inequality. And note that equality does occur, like if you had 6 plus 6 here, that would be equal to 6, and then 6 times 6 would be 36, that would be equal to 6. So equality occurs if all of the sum ends are equal to each other. All right, so let's move along. Now, most of the rest of the work I've already done for you. I applied the AMGM twice. Okay, I applied the AMGM to the reciprocals and to the numbers themselves, because that's what we have here. We have some reciprocals. All right, now you can multiply inequalities just like you can multiply equalities. All right. Now, when you do that, you get a very nice result. You might think initially you have to do least common denominator, or at least, something like that, but you really don't here. Notice that what happens here is because of properties of radicals, this is just equal to 1, right? Okay, again, when you juxtapose these two radicands, everything just cancels, right? And that's just a property of radicals in general, it's the rule that goes like this. We'll put 4 here if you want, but the 4th root of AB is certainly equal to the 4th root of A times the 4th root of B. I don't think there's any exceptions here to this. I don't know if it makes much difference in this rule. If the index is I should have written an A there. That should be A. Okay, and then we have the 4th root of B right here, folks. Let me test the eraser real quick here. Okay, there's always something stubborn like that. I'm not quite sure about this Microsoft product sometimes. Okay, so let's put, this should be an A right here. All right, and so that's all that really happened right here, folks. That's where this 1 came from, okay? Now, what we can see pretty quickly is that you're going to have, when you multiply through by 16, all right, you're going to end up with this result, and I'll just write the result down, and I think you guys can all see it. You get 1 over 20 plus 1 over 21 plus 1 over 22 the sum of the reciprocals plus 1 over 23 okay. Okay, now, so we have this written down now. The sum of these numbers, 20 plus 21 is 41. 41 plus 21 is 63, and then 63 plus 23 is 86. And so what we'll have here is that this is greater than 16, because remember we have to, if you multiply through by 16, and then divide by this sum right here. Now again, this sum, 20 plus 21 is 41. 41 plus 22 is 63. 63 and 23 is 86, right? But notice that this actually reduces to 8 over 43. Okay. And so what was it we were trying to prove? That's what we were trying to prove, right? We're trying to show that 1 over the sum of the reciprocals is greater than 8 over 43. And we have done that. And so let me write down a QED right here. If it even merits that. Okay, so I think it's cool because you see, if you first look at something like this, just the least common multiple, the greatest, or the least common denominator is going to be a huge number here because you have a prime number right here, for example. So this, whatever your least common denominator is probably, you're talking 4 or 5 digits, right? But you never really had to do any big calculations here. And it's because of this double application of the AMGM inequality. We applied AMGM once, twice. Okay. Inequalities behave much like equalities. You can multiply the left-hand side together. You can multiply the right-hand side together. That's this statement right here. And the rest of it is just plain old arithmetic. Okay, folks? So we proved what we set out to prove. Hope you enjoyed.